Hello, physics students. So here is a problem that causes lots of pain and suffering at times. That's the bank curve. So in the bank curve, you have this situation where a car is driving around a circular curve in the road. And the question is, how much do you need to bank the curve so that like the ideal banking angle would be whatever speed the cars are traveling at. They don't have to, the tires don't have to apply any frictional force for the centripetal acceleration that has to happen going around this curve. So I'm going to take the car that's on the curve and I'm just going to represent this bank as such. And we're going to draw, I guess I'll draw the back side of the car here, or at least attempt to do that. Maybe throw a trunk and a bumper and a couple of wheels there. So, top to the car. That sort of looks like a car. Maybe put a little emblem back there on the back of it, or a license plate or something. Still doesn't look like a car, but anyways. So when we analyze the forces that are involved here, you will have gravity, which is straight down, and you will have normal force, which is applied at an angle perpendicular to the road. And the thing to realize here is that gravity cannot provide the centripetal force. So we're used to dealing with ramps and breaking or finding the x and the y components, the perpendicular and the parallel components to do this. But gravity doesn't point inward toward the center of the circle. The normal force points inward toward the center of the circle. So this creates kind of a weird situation where the normal force needs to be, you need to find the components of the normal force. Okay, so whatever the banking angle is, we'll call that theta, is the same as the angle down here. Okay, so and the other thing to realize then is that let's see, n cosine of theta is going to have to balance in the vertical direction. So n cosine of theta is actually going to be equal to, because you're not sliding down or up the banked curve. So n cosine of theta is going to be equal to mg. And I'm talking about magnitude here as well. If you're actually summing the forces, I guess the force sum in the horizontal direction, or excuse me, not horizontal, the vertical direction, it has to be 0, so it would be like n cosine of theta minus mg. Which some AP reader somewhere might be looking for one day. All right, so you have that relationship, and then the other relationship that you need comes from the horizontal direction, and that's going to be where your centripetal acceleration is happening. So that's going to be mv squared over r, and that's going to be equal to n sine of theta. All right, so let me put that in, get the right color here. All right, so at some point, if you're asked to solve for the angle, you might find it useful to be able to come up with an expression for just n. So we can come right here and use this. Oh my. You can use this to get that n equals mg divided by cosine of theta. And knowing that, we can substitute that in place of n here in this expression. So you can get mv squared over r equals mg sine of theta over cosine of theta. Now, some useful things happen here. Masses cancel out. And also, you might know that, and it shouldn't surprise you that the mass of the car cancels out because the bank curve would have to work for, all cars that use the road. But anyways, sine of theta over cosine of theta is tangent of theta. And then you can move the g over to the other side, so it's like v squared over gr equals tangent of theta. And then you can take the inverse tangent to solve for the angle. All right, so I hope that helps with your banked curve.